difficult. Write down the systematic partition function. Okay, so you can clearly see that B requires information from A. Okay, and then I say, okay, then calculate the U of the system. Then you need to have the information at B to calculate UC. Okay, and then if a U, okay, then calculate the G of the system. Okay, then you need information above to get your final answer. Okay, if you get stuck in certain step and you feel like you can just solve this, fine, come to me. I will just grade this one for you. Okay, and I will give you the correct answer for that. So you can continue, but you won't get the grade for this part. Clear? Okay, so you have 4 these questions. It's all like this. Okay, so but it's like from easy to difficult. Okay, I say I'm going to give you 70 points if you study all the material in the lecture, right? If you know your homework, if you know your lecture, if you know your midterm. These 2 is pretty much the things you should get. These 2, maybe actually all the way to C is actually the point you're going to get. But D is really depending on your understanding of the material. Alright? So, you have 4 this type of questions, okay? If you get stuck, okay, don't stop here, okay? Do other A, B first, so you won't run out of time. Okay, so make sure you get at least those 70 points in the beginning, okay? And then you do C and D to test how well you understand the material. Are we clear? Okay. All right, so the first chapter. Anyone has tissue papers? No, I just need to erase them. Cool. All right. Okay, so the first chapters, which is the statistical thermodynamics, what's the first thing you need to know? Is Boltzmann distribution, right? Okay, so the Boltzmann distribution tells you what is the possibility that you observe the molecule exists at specific states, okay, among all the states. So Pi is going to be equal to Ni over N, which is going to be equal to exponential negative beta Ei over summation exponential minus beta Ei. Okay? And this one is equals to okay. This is the population of a molecule exists at I state over the partition function, which is sum of every single states. That give you the possibility. Okay? So you need to know Pi is equals to this, equals to this, equals to this. Okay? You need to remember this. Okay? And the beta is 1 over ABT. Okay? So this little q, we call it as a molecular partition function, right? Molecular partition function. And typically q is actually a product of qt times qv times qr times qe. Okay? You need to have this concept. And to convert the molecular partition function into system partition function Q, okay? So Q is the systematic partition function, okay? This is going to be equals to Q to the nth power divided by n factorial. If A is indistinguishable, okay? If A is distinguishable, then you should just write okay, so this for the distinguishable one. Okay? So when you read the question, be very careful. If I ask you for the distinguishable one, this is your systematic partition function. Okay? So be very careful about this. Clear? The bottom one is distinguished. Okay. Okay, so with this, okay, there's one very important application of the TI, right? Because once you know the TI for example, you have two-state system, okay? And if you know the TI, you know the relative population between the two, right? Okay, so in the hangout, okay, we give you some examples, okay? We say if the energy separation is this, at this temperature, what's the ratio, what's the population between state 1 and state 2, okay? You need to know the calculation. It's very important. All right? Okay. So if you have indistinguishable molecules, okay, you need to know how the U, S, A, and P is related to your Q. Okay? You need to remember this. Okay, it's very important. Okay, so U is equals to negative D natural log Q T beta. S is equals to U over T plus KB times natural log Q. And A is equals to negative KBT natural log Q. And P is KBT partial natural log Q partial B at constant T. Okay? So you need to know this. Alright? So these are the very important things that you need to know for this chapter. Yes?
Or not?
17. I don't really remember which chapter. The chapter after. This is statistical thermodynamic chapter. All right. Any questions for these chapters? Okay. So let me remind you again, all the examples I give in your hangout, they are all very important. You need to know those examples. Okay? Okay, so let's talk about the next chapter, which is the phase diagram. Okay? So in the phase diagram, or phase equilibrium chapter, we introduce a concept, mu. Okay? You need to know the potential mu. Okay? So that's first thing you need to know. And then you need to know how to calculate the degrees of freedom. Okay? So the phase rule is F is equal to C plus P minus 2. You need to know how to use this. Okay? For example, if today I give you a phase diagram, you have the solid, liquid, and gas phase, right? So the degrees of freedom to describe the solid, liquid, and gas phase, you need 2 degrees of freedom. Okay? If you describe the line between solid liquid or solid gas or the gas liquid, the degrees of freedom is just equal to 1. For your triple point, there's no degrees of freedom. Okay? Those concepts are very important, and you should also know what's the corresponding procedure from you change from one phase to the other. For example, if you change from liquid to gas, you know this is called the vaporization, right? And then okay, you have many possible combinations, you need to know all of them, right? Okay, so the very, very important of the phase diagram will be, in the class, we spend a lot of time to describe this, and this, right? We actually derive the mathematical expression for each of them. Okay, you need to remember those equations because you are going to use them to do the calculation. Okay? So for the solid liquid line, Okay, for the solid liquid, the equation you need to remember is actually delta V over delta H. P2 minus P1 is equals to natural log P2 over P1. Okay? For the gas solid or the gas liquid, okay? The equation you need to use is actually natural log P2 over P1 is going to be equals to delta H over R 1 over T2 minus 1 over T1. Okay? The things you need to be very careful here is actually the delta H. Okay? What delta H you should use? There are two different types of delta H here. Okay? One is the delta H of separations. The other one is actually delta H of sublimations. Do you know how to calculate those things? Okay, so you have delta H and delta H. Okay, separation and sublimations. Okay. And then you should also know, like in the class we say, if you have these 2 points of one line and 2 points of the other one, then you can actually solve for the where is your triple point. Okay, this is very important question. Yes.
What are these two mix and not? Gas to solid would be something.
Okay. So you need to know how to solve for triple point. Very important. Alright, so the very last important concept in this chapter is actually, you actually have this one in your homework. Okay, so assuming today you have a system, and inside the system you have some liquid. Okay, so this liquid is going to produce some vapor pressure. Okay, if today you put in a high pressure of flowing gas, okay, how would the vapor pressure of this guy changes? Okay. So the question you to remember for that question is, the equation to remember for that question is actually this, right? Right? So if you know how to calculate all these things I just described, that should be pretty much for this chapter. Okay. Any questions?
So this is just a more general question. Since you're just doing 4 questions over the 4 chapters that we most recently covered,
Yes.
there's not going to be any questions explicitly from the first exam's chapters. Like,
If I
obviously
ask-
you have to know the information, but specific questions from that chapters, from those chapters.
I would say all these 4 questions for these 4 chapters, they are very specific. Okay, that means if you know the knowledge I have told you during the class, you should be able to answer these 4 questions without any problem. Okay, so the knowledge you need to know for the first half of this semester, okay, those knowledge will contribute to question number 1. Okay? Yes. Not just equations. Okay? So number 1 will contain multiple equation will be 1, of course. Okay? So you might expect some questions just asking for short answers. Okay? And those questions will be very similar to the question very similar to the questions you see in the midterm. Okay? That means if you know your midterm really well, okay, and if you know all the questions I asked you to remember in these 4 chapters, you get all the elements for question number 1. Clear? All right. For example, true, false, undetermined may appear in your question number 1.
No. When you mean undetermined, does that mean like, that doesn't mean we have all of them? Yeah. Like true or false is like, it's pretty absolute. What is undetermined?
Undetermined is actually, if I tell you in the class, okay, this is only true under very specific condition, okay? That's what I call undetermined. Okay? If you are in the class, you'll know what I mean by undetermined. Okay, I make those things very, very clear, okay? For example, how to determine S is equals delta H over T. This is only true when you are under phase transition, right? So if I say delta F, you can say delta S equals delta H over T without any other statement. This should be undetermined because there's nothing wrong with this statement. Okay, but it's only true under very specific conditions that it's undetermined. Alright? Okay. Number 3. Solutions. So solutions, the first thing to know is actually we only deal with binary solution. Okay? So when we talk about binary solution, the first thing we talk about is actually Rouse law. Okay? And Rouse law is critically important for this chapter. Okay? All the example I gave you for the Rouse law, you need to master that. Okay? For example, I give you, if you mix 2 materials, okay, I give you, okay, the vapor pressure of pure A, vapor pressure of pure B is this and that. Okay, assuming they follow Rouse law, can you make the figures I make in the class? Can you make the PV plot yourself? Not PV plot, sorry. P versus mole fraction plot. Okay? You need to know how to do that. Okay, it's very important. Assuming you know how to do that, then okay. So then I will ask you, okay, at this pressure, okay, what is the chemical composition of your solution? You should know that, okay? At this pressure, what is the chemical composition of your solution? At this pressure, what is the chemical composition of your gas? Okay? So all those information you need to know how to calculate. Okay, and is critically important for this chapter. Okay, and the equation you need to remember for this chapter will be what? The Rouse law. P is equals to Pi is equal to Pi star times your mole fraction. Okay, Xi. P total is equals to summation of Pi. Okay, and then Henry's law. Pi is equals to Kh times your Xi. Okay, is equal to Khm times your Mi. Okay, so all these things you need to remember. Okay. Mole fraction of B in the vapor phase is equals to P total over Pi, which is equals to Pi star times your mole fractions over P total. Okay, this one you need to remember. So I would suggest you look at that example I gave in the lecture very carefully. Okay, so like get familiar with that because those are the concepts I want you to know. Okay? And then we talk about this is for the ideal solution, right? And we talk about the non-ideal solution. Okay? If you have a non-ideal solution, how would this figure change? You need to know that. Okay? And I emphasize that the things you should really pay attention to including, okay, if it's very concentrated, it should look like your ideal solution, right? If it's very dilute, okay, it will deviate from your ideal solution, but it will be linear, okay? And then in between, okay, it will change whatever way you want to change. You can go up, you can go down, okay? But if I ask you to draw things in the non-ideal condition, okay, you need to specify those regions, okay, to show that you actually know, okay? And you should also know, okay, if you do the extrapolate of this very dilute solution, you will hit the K here, okay? So that's for the Henry's law, okay? And then we describe, okay, how do we describe things happening in between these two extreme cases? You use activity, right? So now you should know for all the components, okay, you can always write your mu I equals to mu I naught plus RT natural log AI. Okay, so this is always true and you should remember this. Okay, and then the AI is going to be equals to gamma I times your Xi. So AI is your activity. Gamma I is your activity coefficient. Okay, Xi is actually your mole fraction. Alright, and you should know for the ideal gas, ideal solution. Okay, for the ideal gas, your A is going to be equals to just your P, right? Ideal solution, your A is going to be equals to A is equal to what?
X for the M, or M,
It's also P.
or gas solution.
Okay. Of course, this is, oh, sorry, P. It's U, Xi. Okay. And what's the gamma? 1. Okay, so this one should be, you should be very certain about this, okay? If you have ideal gas, ideal solution, gamma equals to 1, okay? This is very important. For the non-ideal, gas, okay, then your A is equal to, of course this should be over P naught, okay, but P naught equals to 1. This is over 1 because your composition complete is 1, okay? And this one is actually if you gas it over your P naught, okay? For your solution, your A is just equals to your Pi over P star. Okay? So what's the gamma? Gamma is equals to F over P, and the gamma here is equals to Pi star times your mole fraction Xi. Okay, so the things you should always remember is actually A is always real over a reference, okay? Activity coefficient is real over ideal, okay? So this concept, remember this. Otherwise you'll get so confused. Okay. So use this as an example, okay? For the ideal gas, A is equal to P over P naught. P naught is actually your reference state. Okay, Xi over 1 is your reference state. For the non-ideal gas, if you guess the over P naught is your reference state. Okay. For your solution, it's a Pi over P star. P star is actually your reference state. Okay. For the activity coefficient, okay, you can see the gamma is actually F over P. Okay, P is actually the pressure of your ideal situation. So it's actually real over ideal. Okay. Here, for your non-ideal solution, it's actually Pi over Pi star times Xi. This is a Raoult's law, right? So this they tell you what is the vector pressure if you have an ideal solution. So up is real, bottom is ideal. It's always real over ideal that gives you the gamma. A is always real over some reference states. Okay? Okay, so the very last important concept of this chapter is that we talk about if you mix two things together, what is your delta Hi, what is your delta Si, what is your delta Vi for ideal solution and non-ideal solution, right? That part, you need to know the concept. Okay? Alright, then we can go to the next chapter, which is the chemical equilibrium. So in the chemical equilibrium, the first important thing you should remember is actually your delta G naught is equal to negative RT natural log K. Okay? This is always true, and you will definitely use this equation for many calculations. Alright, so in your homework number 10, okay, now many times, okay, the question asks, okay, if you know this G naught, estimate some equilibrium constant. Okay, sometimes the equilibrium constant, we call it actually Henry's law constant. Okay, so in your question number 4, I ask, okay, please estimate the Henry's law constant. Okay, and the only information I give you is actually the temperature and the delta G naught, right? Then you should ask them at the K using this equation. Okay? Alright, so that's the first thing you need to remember. This equation, you need to memorize it, okay? It's very important.